Okay, welcome back. Uh, in this video, we're going to cover Unit 2A of the uh, midterm review. So let's just get right into it. Let's look at number one. We want to find an equation that gives the nth term of each sequence. Um, let's see. So first, we need to remember um, what our formulas are for this. So we have that a sub n is given by a sub k plus d times n minus k. So for arithmetic sequences, given a k value, so that signifies what term we're going to use to base our formula off of. So in this case, k is equal to 1. Uh, then this would be k is equal to 1, k is equal to 2, k is equal to 3. So this k just signifies what term we're going to use to base our formula off of. But this goes for arithmetic sequences when we're adding or subtracting some common number to get from one term to the next. And then for geometric sequences, we have g sub n is equal to g sub k times our common ratio to the power of n minus k. So similarly, k signifies the same thing in each of these. And so and remember, geometric sequences are when we are multiplying or dividing by some common number, but we always want to frame it as multiplication. And so, with these two formulas in mind, remember you're going to have to remember these on your exam. I will not be providing you any formula chart. Um, let's look at number one. Let's see what kind of sequence we have. So, we can see that to get from -2 to -8, if we were adding some number, this would be subtracting 6. But if we subtract 6 again from this, we don't get 30 or -32. So we know that this can't be arithmetic. Now, what about geometric? So to get from -2 to -8, we have to multiply by 4. And then to get from -8 to -32, you multiply by 4. And sure enough, if you multiply that by 4, you get to -128. So this is definitely a geometric sequence. So we know that we want to use the formula g sub n is equal to g sub k times r to the power of n minus k. And this problem is telling us to use k is equal to 1. So that makes our formula g sub n is equal to g sub 1 times r to the power of n minus 1. And again, what was the value that we were having to multiply every time? We were having to multiply by 4 every time. So we know that our ratio is 4. We know that k is equal to 1. Now we just need to establish what g sub 1 is. Well, g sub 1 is just the first term of the sequence. So g sub 1 is -2. So piecing all of this together, that gives us that g sub n is equal to -2 times 4 to the power of n minus 1. And so this formula here will give us any term in the sequence. So if we wanted to find g sub 3, for example, all we need to do is just like a function where we evaluate g of n. If we evaluate g of 3, all we have to do is replace n here with 3, and it'll give us this term. And you'll see we're not being asked to find a specific term in any of this, but just to really hammer that idea down, if I replace n with 3 in this, then this is going to be -2 times 4 to the second power. And so 4 squared is 16. And we see that that's -32, which corresponds to our third term. So we know that this formula is correct. Okay, so now what about number 2? So we want to see, is the sequence arithmetic or geometric? So if we go from 325 to 225, by addition, that would be subtracting 100. And then 225 to 125 is also subtracting 100, subtracting 100. So we know that this is arithmetic. We don't even need to check if this is geometric. It's either going to be one or the other. So we know that our formula is a sub n is equal to a sub k plus d times n minus k. And we're given that k is equal to 4. We're given that our common difference is subtracting 100. And so really, we just need to identify, well, let's see, we have a sub n. Since we're using k is equal to 4, we have a sub 4 plus d times n minus 4. So now let's just replace d with our negative 100. And then let's replace a sub 4, so the fourth term in the sequence 1, 2, 3, 4, a sub 4 with 25. And when we do that, we have a sub n is equal to 25 minus 100 times n minus 4. And that is our final answer. So for this next one here, so let's check if this is an arithmetic sequence or a geometric sequence. If we're starting with negative 25, then we have to add 6 to get to negative 19, and then we have to add 6 to get to negative 13. And so we see that this is arithmetic with a common difference of positive 6 because we're adding 6. And we also know that the formula that we want to use is a sub n is equal to a sub k plus d times n minus k. But where k is equal to 0, so if k is equal to 0, then this formula simplifies to a sub n is equal to a sub 0 plus d just times n, because n minus 0 is going to be n, so we just have dn. But we don't have a sub 0 listed in this sequence. So what we're going to have to do is figure that out. And so we know that if our common difference, if we're adding 6 every time to get from one term to the next, then to work backwards, we need to subtract 6. So negative 25 minus 6 is going to give us that a sub 0 is equal to negative 31. And so now we can just piece this information together, and we have that a sub n is equal to negative 31 plus 6 times n. And so this is our formula. Now, what about number 4? To get from one term to the next, are we adding or subtracting any number? Well, to get from 16 to 4, we have to subtract 12. But 4 minus 12 is not 1, so this is not arithmetic. And just to confirm that it's geometric, to get from 16 to 4, we have to divide by 4. 4 divided by 4 is 1. 1 divided by 4 is 1/4. So we see that our common ratio is multiplying by 1/4. Remember, we always want to phrase this as multiplication. So dividing by 4. So you could say this is multiplying by 4, or you could say it's division by 4, but we don't want to use that. We want to say that this is multiplying by 1/4. So now, so the formula that we want to use is g sub n is equal to g sub what? Well, we have k is equal to 3, so this is going to be g sub 3 times our common ratio of n minus 3. And so we already know what our common ratio is. Let's just figure out what g sub 3 is, which is, in this case, 1. So since g sub 3 is equal to 1, we just piece this information together, and we'll have our formula. So we have g sub n is equal to g sub 3, which is 1 times our ratio of 1/4 to the power of n minus 3. And because we don't actually need this 1 here, we can just simplify this and write it as 1/4 to the power of n minus 3. Something to note here is that please be sure to put parentheses around any fractions for your ratio, because if you have some fraction a over b to the power of n, this is not equal in general to a divided b to the power of n. Well, at least it's not clear that of what you mean here. Because what this looks like is that you have a to the power of n and then divided by b. So just to be clear that that n has to be applied to the b as well, just put your fractions in parentheses, so it's more of a clarity thing than anything. But that concludes the first 4 problems. Let's look at the next one. So I'm going to find the nth term of each sequence. So first, we need to find a common ratio, or sorry, not a common ratio, a formula that generates each of these sequences. So let's see, if we're starting with 117, to do adding or subtracting, looks like we have to subtract 11, subtract 11, subtract 11. So our common difference here is minus 11. And that means that we have an arithmetic sequence. And because they didn't tell us what k value to use, we're free to use whatever we like. So a sub k plus d times n minus k. I'll choose k is equal to 1. Let's base it off of this first term. So that means that a sub n is equal to a sub 1 plus d times n minus 1. So if I'm letting k equal 1, this is the formula we're going to work with. And then what is a sub 1? Well, a sub 1 is equal to 117. And so now we just need to plug this information into this formula here. And we get a sub n is equal to 117 minus 11 times n minus 1. So now that we have a formula, we want to figure out what is the 47th term. And so this is a pretty good time to whip out the calculator, because if we're going to figure that out, the 47th term is going to be a sub 47 is equal to 117 minus 11 times 47 minus 1. And if we simplify that, so plugging this into your calculator gives you negative 387. And so this is our 47th term, negative 387. All right, so what about number 6? We want to find the 401st term. Okay, so it's going to be a really big number. Let's see. So for each of these terms, we're adding 5 to each one. So since we're adding 5, our common difference is equal to 5. And since this is an arithmetic sequence, we have a sub n is equal to a sub k plus d times n minus k. And again, I'll use, I don't know, it doesn't really matter. Sure, the third term. So we can do a sub n. If k is equal to 3, then we have a sub 3 plus d times n minus 3. And the reason that I can pick any term is that this formula works for whatever term you're using, as long as you just replace k with the same number. So if you're going to have this as a sub 3, then this just has to be n minus 3. But that's kind of the nice thing about this, is you don't actually it doesn't actually matter which term you base your sequence off of. It'll give you the same answer regardless. So usually you pick one for whatever is most convenient. I'm not necessarily picking one for convenience, but more so to illustrate that we can pick any term that we want. We don't have to stick with 1 or 0. But with that in mind, we see that a sub 3 is equal to negative 14. And so that means that a sub n is equal to negative 14 plus 5 times n minus 3. So this is our formula, and now if we're going to find the 401st term, we just need to replace n with 401. So a sub 401 is equal to negative 14 plus 5 times 401 minus 3. And going back to the calculator, so just typing that in. So typing that in, and we get 1,976. So that is the 401st term to this sequence. All right, let's look at 7 through 9. So we want to know, could this function, could these points be connected by a linear function, an exponential function, or neither? So let's see. So what's nice is first we need to confirm that our x values are increasing by the same amount every time. So 4 to 5 to 6 is all increasing by 1, so that's good. And then let's see. 6 plus 4 is equal to 10, but 10 plus 4 is not equal to 18. Let's see if we're multiplying by some number every time. Well, to get from 6 to 10, we have to multiply by 10 over 6 to get 10. Now, do we have to multiply 10 by 10 over 6 to get to 18? And no, we can't do that. Or at least, not that we can't do that, it's just, it's not true. So, this is neither. Now, what about number 8? We have, let's first confirm our x values, 1, 2, 3, so we're all adding by 1. Let's check arithmetic first. So 3 plus 9 is equal to 12, but is 12 plus 9 equal to 48? No. So this is not arithmetic. Now, what about geometric? Or, sorry, we're using linear and exponential. So this is not linear. Now, what about exponential? Let's see, well, 3 times 4 is equal to 12, and 12 times 4 is equal to 48. So, since we are multiplying by 4 every time, this is an exponential function. Again, with number 9, let's confirm that the x values are going up by the same number every time. We have 16, 17, 18, so that's good. Now, let's look at the y values. So we start with negative 5. So let's check for linear. If we if we add 4 from negative 5 to negative 1, so adding 4 gives us negative 1, and adding 4 again does give us positive 3. So because we were having to add 3 every time for our y values, this is a linear function. Okay. And so for number 10, pretty similar idea here. We're just trying to figure out, is this linear or exponential? Well, let's see how our x values are changing first. We have to make sure that these are consistent. We see that this is going up by 5, and we see that this is going up by 5. And so that's good. So now we can actually check if it's linear or exponential. If they are not going up by the same amount, that complicates this, and then our method here doesn't actually work. So now we have to see, well, let's see, if we're doing addition, 3 plus 9 is equal to 12, but 12 plus 9 is not equal to 48. But if we're doing multiplication, we have 3 times 4 is 12, and 12 times 4 is 48. And so, because we are multiplying by 4 every time, this is an exponential function. And it's asking us to justify y. And it's exponential because for each input change of 5, f changes, and here's the key word here, proportionally by a ratio of 4. So our key word here is that it changes proportionally for each input change of 5. But this is our justification for it being an exponential function. Now, what about number 11? So how are our x values changing? Well, this goes up by 4, and this goes up by 4. Okay. And now, how is this changing? Well, let's see, to go from 12 to 5, we can subtract 7, and then from 5 to -2 is also subtracting 7. So, we see that this has to be a linear function. But why? Well, this is linear because for each input change of 4, f changes at a constant rate of -7. So this constant rate part is the key word for this being a linear function. So when you're asked to justify whether a function is linear or exponential, this is the wording the College Board is going to be using, or that they're going to be looking for. All right, let's look at number 12. So we want to identify, is this a linear or exponential function? And then we want to identify the constant, the slope or ratio that causes the output values to change. So remember, exponential functions are of the form f of x is equal to a times b to the power of x. So I'm going to scoot that over a little bit. And linear functions are in the form of f of x is equal to m times, well, I'll use a times x plus b. So anything of either of these forms is going to be, this is going to be exponential, this is going to be linear. And notice the placement of your x. So for exponential functions, we have some number raised to the power of x, and we can translate that left or right, so adding or subtracting a number from x. And similar thing for linear functions, but notice we have a number times x, and then we can add or subtract some number. So when we're trying to figure out, do we have an exponential or linear function, I think personally the easiest thing to do is to identify, well, do you have an exponent that is a variable, in this case x? And yes, we do. So for number 12, this is exponential. And so what is the constant that is causing the output values to change? That is going to be 2 or 3. So we would say that this has a ratio of 2 over 3. That's what's causing this function to change. It's whatever your base is. But this linear function here, we know it's linear because it has a number times x plus or minus another number. And so this is linear, and the number that's causing it to change is this 9, what's right next to the x. And so this has a slope of 9. Now what about this function? So it looks a little bit crazier. However, just by looking at it, we can tell, well, this does have a power of x. So we have 2 to the raised to the power of x minus 5. That already tells us that this is going to be an exponential function. And even if we rearrange this, we could write this as y equals 1/4 times 2 to the power of x minus 5 plus 6. And even though we have a more complicated looking expression, we still have a number times a number to the raise to a power of x, and then plus or minus a number. That's just going to be a translation up or down, but it doesn't change the fact that it's an exponential function. Because again, we have this power of x. So this is still exponential. And the number that's causing it to change the output values is this base here, this 2. And so this is going to be the ratio of 2 that is causing our y values to change. Lastly, what about number 15? So again, this looks a little bit more complicated, but we see that we don't have any exponents with an x in there, or any exponents at all, really. However, we do have this 3 times x. And even if we rearrange this, we can rearrange this as y is equal to 3 times x plus 18 minus 5, which is just 3x plus 13. And so now that this is in a more familiar form, now in order to identify whether something is exponential or linear, you don't need to rearrange it and show me that if you're able to just identify it. And I'm not really looking for much work on that if I do ask you any questions like that. However, this is definitely linear because we have a number times x, and it has a slope of 3, and that's what's causing our y values to change. All right, so let's look at number 16. We know that f of x is a linear function and it passes through the given points. We want to find an equation for this function. So if we know that a linear function connects these 2 points, we need to find the slope between them. So our slope is going to be given by this y2 minus y1 divided by x2 minus x1. Need to know this formula. You should definitely have it memorized by now because this is something we've seen since Algebra 1. But plugging in these values, I'm going to choose this point to be my x2, y2, and this point to be my x1, y1. Because it doesn't really matter which point you assign it to be, but what I would like to do is basically keep so what we're going to do is we're going to have 5 minus 85 divided by 13 minus 8. That gives us negative 80 divided by 5, and negative 80 divided by 5, that's going to be negative 16. So our slope is negative 16. And now that we know our slope, we want to use our point-intercept form, where x naught and y naught could be either one of these points, so it doesn't matter which one you plug in. And so I like to work with smaller numbers, so 13 comma 5 seems like a good one to plug in. So whatever the y-coordinate is, so y minus 5 is equal to negative 16 times x minus whatever our x-coordinate is, which is 13. And you don't even need to simplify this, you can just leave it as is. And this will be our answer. You could have also plugged in the other point, and you would get y minus 85 is equal to negative 16 times x minus 8. And either one of these formulas works. In fact, if you simplify them and write them in the form of y equals mx plus b, they will actually be the exact same thing. Now, what about number 17? Again, we want to find the slope between these 2 points if we know this is a linear function. So that's going to be 20 minus 8 divided by 4 minus 2. Now 20 minus 8 is going to be 12, and 4 minus 2 is 2, and that simplifies to 6. And now we want to use our y minus y naught is equal to m times x minus x naught, so our point slope form. And so now we're just going to plug in either one of these points. I would personally pick 2, 8 because smaller numbers are always nicer. But we have y minus 8 is equal to our slope 6 times x minus 2. Katie, I'm busy. I'm sorry. And so this formula works, or we can plug in the other point, and you could have y minus 20 is equal to 6 times x minus 4. And this formula will work as well. So either one works, it's up to you, and it does not matter to me. All right. Now, what about these? Now we have an exponential function. Okay, so we have an exponential function that connects these points, but what is a exponential function that connects them? So we can figure that out by first, we know that when we take 85, how many times are we going to have to multiply 85 by some common ratio to get 5? Well, it's going to be determined by whatever this distance is, because think about this if we set it up as a table. So if this is 8, 9, 10, 11, 12, 13. So for 85, 8 comma 85 we have over here, and then we have 13 comma 5. Now, we don't know what these values are here. However, because this is an exponential function, we know that we have to multiply it by some common ratio every time that I'm going to call b. And so, if I have 85, I have to multiply by b to get this next point, 9 comma something, and then multiply that by b to get 10 comma something, and blah, 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 blah. And basically, we can set up the equation 85 times b times b times b times b times b. So 5 b's, so times b to the 5th. Well, we multiply it by our common ratio 5 times, and we get 5 out of this. And instead of having to set up a chart like this, what you can do is just recognize that, well, 5 is the same thing as 13 minus 8. So if we set up this equation and solve for b, we're going to divide by 85 on both sides. That's going to give us b to the 5th is equal to 1 divided by, was that 17? I think so. Probably. And then we just have to take the 5th root on both sides, and that gives us that b to the 5th is equal to the 5th root of 1 divided by 17. So, sorry. I wrote b to the 5th, but b is equal to the 5th root of 117. Okay, so now that we have our common ratio, this is the hard part, and that's done. Now we just need to plug this back into our formula. So the formula that we're going to use is basically that y is equal to y naught times our common ratio to the power of x minus x naught. And doesn't that look very, very familiar to our geometric sequences? But plugging that in, that means that y is equal to whatever point we want. I'll use 13 comma 5. But 5 times the 5th root of 1 over 17 to the power of x minus 13. And that means that we can also use the other point, and we have y is equal to 85 times the 5th root of 1 over 17 to the power of x minus 8. And both of these formulas will work. Next, let's try number 19. So, same thing. We want to figure out what is our common ratio. Well, start with 8 and times b. How many times to get to 20? Well, 2 and 4, they're 2 units away, so 4 minus 2 is 2. So we have 8 times b squared is equal to 20. And that means that b squared is equal to 20 divided by 8, which is, let's see, both of those are divisible by 4, so equal to 5 over 2. And so if b squared is equal to 5 over 2, then b is equal to the square root of 5 over 2. Now, normally we would say when we take the square root of both sides of an equation like this that b is equal to plus or minus the square root of 5 over 2. We actually don't want to do that. That's going to make things kind of complicated if we consider a negative base for this. Don't do that. So let's stick with the positive solution to this. But now that we know that that's our base, we're going to use the same formula over here. And we have that y is equal to, let's see, if I use this point over here, that'd be 8 times the square root of 5 over 2 to the power of x minus 2. Or we can use y is equal to 20 times the square root of 5 over 2 to the power of x minus 4. So either one of these formulas work. Okay, so let's look at the next problem. So for number 20, let's see, we want to identify the exponential function, blah, 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 is growth or decay, and justify your response. So we need to recognize that this function is in the form of f of x is equal to a times b to the power of x. And so, let's see, growth or decay is going to happen. Well, first of all, we have to see that a is a positive number. So we can determine whether it's growth or decay now just based off of what the base is. So remember that we have growth if b is greater than 1, and we have decay if b is between 0 and 1. And so we need to identify what a and b are. So here a is equal to 0.6. We have b is equal to 5.25, which is greater than 1. Therefore, it is exponential growth. For number 21, we want to find the value of that. So this is an alpha value of an exponential function of the form x equal to b, or f of x equal to a times b to the power of x. Write the function along with the input value that represents the output value. Okay, so we have 3 times 3 times 3 times 3 times 7. One way that we can write that is 7 times 3 to the 4th power. And wouldn't you know, that looks an awful lot like a times b to the power of x. So our function here is 7 times 3 to the power of x, where x is just equal to 4. All right. Now, what about number 22? We have an exponential function. Is this increasing or decreasing? So first, this is where we want to identify, or we want to know what our chart looks like for whether we have exponential decay or growth, and then like how a or b, or sorry, how a, whether it's positive or negative, affects that. Basically, I'm going to make a very small version of that over off to the side. but our function looks like this when a is positive and b is greater than 1. And it looks like this when a is positive and b is between 0 and 1. And then when a is negative and b is greater than 1, our function just looks like this one, but reflected over the x-axis. So it'll look like that. And then lastly, if a is negative, but b is between 0 and 1, then we're going to have a function that looks like that. So if the exponential function is this, all we have to do is identify what a and b are. So we say that a is negative, so we're between one of these two. And since b is 0.6, which is between 0 and 1, we see that our function is going to look like that. And so we would say that this is an increasing function because every time we move to the right, we have to move up. And even though we have to move up less and less, it is still going up on its entire domain. Okay, what about this one? Exponential function. First, let's identify what a is. A is a positive number, so we're between these two. And then we have that b is between 2 and 3. Sorry, not between 2, it is 2/3. So it is this function. And so we want to see, well, is this concave up or concave down? Well, we can see that the concavity of this, it looks kind of like a cup. So this is concave up. Because again, if we draw out our function like this, notice that our rates of change, they're starting off pretty steep. And then as we move further to the right, the slopes are increasing. So that's how we know that it's concave up. And now, what about number 24? So we have to identify what a and b are. So a is a negative number, so it's going to be one of these two graphs. And then b is positive, so it's going to look like this. And so if our function looks like that, as x goes towards negative infinity, so as x goes towards negative infinity, our function is going to taper off and approach 0. And for f of x as x goes towards positive infinity, our function is going to go down. So f of x, I'm going to run out of paper there, but f of x is going to go down as we go further to the right, and so this would go towards negative infinity. Let's look at number 25. So we want to identify the type of transformations that are occurring. So as discussed in class, we can for functions like this one, and this one, we can characterize these very easily as vertical dilations. However, we don't want to actually do that. Now, while a vertical dilation will be a valid way to describe the transformation, I can guarantee you that College Board is not going to characterize any of this as vertical dilations, especially on the multiple choice, when they're probably going to say this is a horizontal translation. So let's just ignore how these are being transformed as or in the context of vertical dilations, and let's see how we can characterize these as horizontal translations. So Let's see, if we know that g of x is equal to f of x times 16, then we know that g of x is equal to 2 to the power of x times 16. Now, what's important to realize is that 16 is equal to 2 to the power of 4. So we can rewrite this as 2 to the power of x times 2 to the power of 4. We want to write these with the same base. That way we can use the property that a to the power of n times a to the power of m is equal to a to the power of n plus m. So if we have this property, we can combine these two as 2 to the power of x plus 4. And now we see that we started off with f of x equal to 2 to the power of x, and now we're adding 4 to x. So what does this mean? That means that we are going left 4 units. Similarly, well, actually not similarly in this case, f of x, let's just plug in f of x into this function g of x and see what happens. So since we have f of x to the power of negative 2, that means we have 4 to the power of x to the power of negative 2. And now we want to use this property that if we have a to the power of n to the power of m, this is equal to a to the power of n times m. And so now that means that basically we can just multiply these two exponents, x and negative 2, and we can make this 4 to the power of negative 2x. So we start off with 4 to the power of x, and then we have 4 to the power of negative 2x. So two transformations are going to happen here. We're going to have a horizontal dilation by 1 over the absolute value of negative 2, which is just going to be 1/2. And then that negative tells us that we have a horizontal reflection as well. And so those are our two transformations that have happened here. Now, what about number 27? So similar, we're just going to replace f of x with 2 to the power of x. Which means that we can write this as 2 to the power of x divided by 4, which we can write as 2 to the power of x divided by 2 squared. And so other property that we want to use, similar to this one, is that if we have a to the n over a to the m, this is equal to a to the n minus m. And so now we can rewrite this as 2 to the power of x minus 2, which means that we have gone right 2 units. And now this last one, we're going to replace f of x with 2 to the power of x. This gives us negative 2 to the power of x divided by 16. And 16 is again equal to 2 to the 4th, so we're going to have negative 2 to the power of x divided by 2 to the 4th, which we can rewrite as negative 2 to the power of x minus 4. The two transformations are happening here. First one is that this negative out in front of our function, in front of the 2, this is going to be our vertical reflection. And the second one here is that we're going to right 4. And so those are our two transformations for this function. Okay, let's look at number 29. So we have that h of x is equal to this. We want to find h of 2. So h of 2, all we have to do is replace x with 2. That's going to give us 10 times 5 to the power of 2 divided by 4. Well, 2 divided by 4 is just 1/2. So really this is 10 times 5 to the 1/2 power. And if we remember our exponent properties, anytime we have something as a 1/2 power, this is that number to the square as a square root. So a to the 1/2 power is the same thing as the square root of a, and that means that we have 10 times the square root of 5. And for number 30, we want to evaluate this function at -1. So h of -1, we're just going to replace x with -1. That means we have 4 times x to the -1/3 power. So another two important properties to recall here. First, if we have a number to a negative exponent, that's going to be 1 over a to the n, which means that we can rewrite this as 4 divided by 8 to the 1/3 power. And next, the other property we want to recall, similar to our exponent properties here, a to the 1 over n is equal to the nth root of a. So 8 to the 1/3 power is the cube root of 8, which is equal to 2. So really we have 4 divided by 2, and that gives us 2. So that is our final answer for number 30. All right. Let's look at the last page for number 31. So below is a table of values for exponential function. In that form, write an equation for this exponential function. So the first thing that we need to do is figure out what our base is. So anytime you have a question like this, find b. So how do you find b? Well, in previous problems, when we didn't have this plus k, we could just see what number we're multiplying to get to one y value to the next. But that's not quite the case here. So what we have to do is we're going to find the common difference between these values first. See, what are we adding or subtracting to get from here to here? Well, this, we have to add 7. Then we have to add 14. Then we have to add 28. Then we have to add 56. And so once we figure out the common differences here, then we figure out how are these values changing multiplicatively. So we see that 7 times 2 is 14. 14 times 2 is 28. Times 2 is 56. And so this tells us that b is equal to 2. And now that we know that b is equal to 2, we can plug this back in to this function here because we know that f of x now has to be in the form of a times b, or sorry, not b, because we found b, a times 2 to the power of x plus k. So let's see if we can set up a system of equations by plugging in 0 and 1 into this function and seeing what we get out of it. Well, we know that when we plug in 0 into this, we get a times 2 to the power of 0 plus k, which is supposed to be equal to 4. Because when we plug in 0, we get out 4. So simplifying this a little bit, we know that 2 to the power of 0 is just 1. So really we have a plus k is equal to 4. And similarly, if we do f of 1, that's going to be a times 2 to the power of 1 plus k, and the y value we get out of that is 11. So simplifying that, we have 2 to the power of 1, which is just 2. So we have 2a plus k is equal to 11. And so now we want to solve the system of equations a plus k is equal to 4 and 2a plus k is equal to 11. So what I'm going to do is I'm going to multiply this top equation by -1. We're going to use the method of elimination. So we have negative a minus k is equal to negative 4. And if I keep the bottom one the same, just by multiplying it by positive 1, this is still 2a plus k is equal to 11. And now when I add these two equations together, I see that the k's cancel, and then negative a plus 2a is equal to a, and negative 4 plus 11 is 7. So a is equal to 7. And now that I know that a is equal to 7, then if a plus k is equal to 4, as I don't write a 4 here, since a plus k is equal to 4, then 7 plus k has to be equal to 4, which means that k is equal to negative 3. And so now, since we know what k is, we know what a is, and we know what b is, we can combine all of that information and see that our function f of x is equal to 7 times 2 to the power of x minus 3. And that is our final answer for this question. All right. And last, we have this is a very much a calculator active problem. So I'll give you a second to pause and read that. Okay. And so after reading this, we want to estimate the number of fruit flies. Let's see, after blah, blah, blah. Anyways, moving on to part A. So we want to use the exponential regression to find, or to model this data. So the first thing that we need to do is we go to stat in our calculator. So let me back up real quick. So how we do this, we go to stat, and we're going to edit this data. Now, I already have it entered in here because I was doing this a couple of days ago with another student. But once you have your data in for L1 and L2, we're going to go back to stat and go to calc, and then we're going to scroll down to exponential regression and hit enter. So it should autofill your x and y list as L1 and L2, and we're going to scroll down to store regression equation, and that's where we want to store the regression equation as alpha trace and hit enter for y1. Now you can store it for any of your variables and in this, but usually you're only working with one equation at a time or one function at a time, so storing it as y1 is usually the way to go. But after we hit calculate, this is going to give us our function in the form of a times b to the power of x. So we see that our function, that a is equal to 2.07, and since we're being asked around to 3 decimal places, 2.078. B is going to be 1.221, because we're going to have to round up, and then to the power of x. And the reason that we stored that regression equation as y1 is because when we go back into y equals on our calculator, now we wrote down the rounded equation, but our calculator stored this up to, well, a lot of decimals of accuracy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 decimal places of accuracy, which is pretty solid. So on your paper, you write down the rounded version of this, but your calculator is going to have the much more exact version of this. So now that we have that in our calculator, we now want to know that according to our model, how many fruit flies were there after 12 hours? And so what that's asking is, what is f of 12? Because 12 in this case is going to be our number of hours, And according to our model, we have values for 10, we have some for 15, and our regression equation is going to, as closely as it can, model each of these values. So now what we're going to do is, since our regression equation is y1, we're going to hit alpha, trace, enter, and then with parentheses type in 12, because that's going to give us our estimate. And we see that f of 12 is equal to about 23. We can't have 0.76 of a fruit fly, so we have to round that to 23. But after 12 hours, we get about 23 fruit flies. Now, you could also say that, well, after 12 hours, there were only 22 fruit flies and not another fruit fly had been born yet, or whatever. But it's kind of up to you. I would prefer to round this because, again, this is an approximation. So I think 23 is correct, but if you put 22, that's fine too. If the model were to continue, so if we look at part C, how many fruit flies would be in the kitchen if he was gone for 3 days? So this is not asking f of 3 because it's saying 3 days and our units are in hours. So what really this is asking is how many fruit flies were after 72 hours, because we have to convert days into hours. But same thing here. We're just going to calculate y1 of 72, and we see that after 3 days, there's about 3.5 million fruit flies, which is hysterical because that's a lot of fruit flies. But 3,586,273 fruit flies. And if we wanted to round that, we could say that's up to 4, because we have, again, 0.76, so rounding up. But, oh, and it says round to the nearest whole number, so there we go. So definitely 274. So yeah, after 72 hours, we have 3.5 million fruit flies. Now, how long before there are 1,000 fruit flies? So this is where we have to go into y equals, and we're going to put into a second function 1,000. And if our standard viewing window, if we try to graph this, our exponential function does that, but y equals 1,000 is going to be 1,000 units up on our y-axis. So we have to modify that in our window. Our y minimum can be 0 because we're never going to have negative fruit flies. But we want our y maximum to make sure that we can see this to be probably about double whatever this number is. So let's just make that 2,000. And now when we graph this, we can see our exponential function way down here, but y equals 1,000 right here. Which should make sense because our window only goes to x equals 10. Well, we see that x equals 10, we only have about 20 fruit flies so far. So we need to extend this window greater than 24 because that's still only up to 200. Let's see what we get if we modify our window to say x minimum of 0, but a x maximum of 40. Now let's see what we get. And there we go. So what we're trying to do is we're trying to find the intersection of these two curves. And so the reason we put in 1,000 is we're trying to figure out, well, where is this exponential function equal to 1,000? And so we're going to use second trace, which is going to pull up calculate, and we want to find the intersection. And our first curve is already here in blue. Our second curve is here in red. And our calculator is trying to guess where these functions intersect. And if you hit enter again, it says it intersects on about 31 hours after so yeah, 31 hours, and let's see, round nearest whole number. So when h is equal to 31, so take 31 hours to get 1,000 fruit flies. And now this part we never really we didn't explicitly cover from in our material, but it's not that hard to do. Use your model from part A to find the error at t equals 10. So your error is going to be just your, I guess if we give it as a percent error, it's going to be the absolute value of your actual value minus your predicted value divided by your actual value and then times 100. This is going to give you your percent error. So I guess let me make that clear. Percent error. And I guess, hold on. Those absolute value bars have to extend all the way down. But yeah, this is going to get your percent error. So to model your error at t equals 10, we just need to look at our graph, or sorry, our table. So our population at h equals 10 means that our actual value at 10 is equal to 20. And what is our predicted at 10? Well, according to the model in our calculator, if we just go to second graph, you see that at 10, we have that number. So about 15.274. So what I'm actually going to do is I'm going to set up a fraction like this. So I'll do math, absolute value. All right, so we have our actual, which is 20, and then minus alpha trace y1 of 10, and then divided by actual, which is again 20. We're going to take all of that times 100. And we see that our error, percent error, was about 23.6%. So let's see, this was y1 at 10. And so putting all that into your calculator, yeah, we got 23% error. Because if we compare this, what was y1 again? Oh, sorry, messed that up. So our actual was 20, but our predicted value, according to the function that we made, was 15.27. So it makes sense that it's about a 23% error. 25% would have been 15. Um, and so the last question is the value predicted an overestimate or an underestimate of the actual value? And so the value predicted was 15.27, but the actual value was 20. So we would say that this was an, let's see, value predicted was an underestimate. And that's it. So you don't have to worry about these last two questions on your exam. Um, that's just more of like an FYI. But anyways, that is that. So, anyways, I will see you later.